Now, I'm going to have another puzzle for you folks to consider. And this involves the happy ball and the sad ball. Okay, so we have the happy ball, which is bouncy, bouncy. And then we have the sad ball. Although I did a program at a school where there was a kid who objected to my characterization. He said, no, this is the happy ball, because it's just hanging out. It's just chilling. It's relaxing. This one is like the unsettled ball. It can't decide what it wants. It can't. And so we can have the unsettled ball and the happy ball. Okay? So we're going to take these. I'm going to roll them down a ramp. I'm going to put a ball here. I'm going to roll it down the ramp, and it's going to hit the block. And when it's going to hit the block, there's going to be a collision, and collisions entail forces. Here's the happy ball, the one that doesn't bounce. And here's the unsettled ball, the one that bounces and can't decide what it wants. Ooh, the one that bounces knocks the block over, and the one that doesn't bounce doesn't knock the block over. And that's a bit of a puzzle. That's a bit of a puzzle that we're going to return to. That will knock the bouncing, good. Not bouncing, not enough. So it turns out, if you have a collision with something bouncy and a collision with something not bouncy, which one exerts more force? The bouncy one. Why does landing with a bounce cause more force than landing with a thud? That's something that we're going to consider. That's sort of a puzzle. Ask this question. Do you want a rebound or not, if you're going to minimize the force and the impact? And we already saw this. We already saw this with these two balls. If you want to minimize the force in the collision, you don't want to bounce. You don't want to bounce. And we can understand why by using the equation. And we're going to use the vector nature of the force that you were talking about. If you have a ball which hits the floor and bounces, here's like before. Here's a ball, and it's got a certain amount of momentum. It hits the floor and lands with a thud. And it's got a certain momentum. And I'm going to call this, let's suppose it has a momentum of 1 kilogram meter per second. Oh, except it's moving downward. So what are we going to, so that's going to be negative, right? So it's actually, the magnitude is 1 kilogram meter per second, but since it's moving downward, I'm going to say Py is equal to minus 1 kilogram meter per second. That's what it is before. What's the momentum after it comes to rest? 0. So what's delta P in this case? It went from minus 1 to 0. The change? 1. Plus 1 kilogram meter per second. Let's suppose it lands and bounces. And so we'll look at this situation right here. The ball is moving downward, and it's got a momentum minus 1 kilogram meter per second. And now let's suppose it rebounds at the same speed. Now it's got an upward momentum. And what's the upward momentum to it if it rebounds at the same speed? 1 kilogram meter per second. What's the change in momentum between here and here? 2 kilograms meters per second. So twice as much momentum change if you have something which lands with a rebound as you do if you have something which lands with a thud. So if your goal is to minimize the force in a collision, landing with a thud is the way to go. Landing with a thud is absolutely the way to go. And that's why, in this case, we have this ball, which lands with a bounce, knocks the block over, and the ball which lands with the thud does not. The force is less.